happens. So these sort of collisions, it can lead to head impact on the structure, on the floor, and head motion, forces, and then eventually damage to the brain. And here's actually the damage that this particular cyclist sustained. So here you can see these little spots. These are called microvilli. So this is the blood that was supposed to be in the veins, but they end up in brain. So it just shows that these veins have been exposed to large mechanical forces, been damaged, and then blood appears in the brain. So that's one way of looking at whether there was damage in the brain or not. Is this kind of imaging modalities, or the susceptibility way to imaging. So the key question is that then how can we predict strain? So in almost last 15 years,
İki tane isim
we
var.
have been
Tek
working
isim.
at Imperial using a method that I'm sure all of you are familiar with, finite element modeling, to develop a finite element model of human brain. So I have been having very close collaboration with Professor David Shaw in brain sciences. He's a professor of neurology. So I had access to his database, MRI scan standard diffusion MRI, which shows the wiring in our brains. Our brain is made of nerve cells. The body of the cell makes the gray matter on the surface of our brain, but then 3/4 of our brain is made of the projections of these cells, which is called axons. So this is the wiring of our brain that transmits signals across the brain and between brain and our body. So what you see here is these wires in different directions going within our brain. So we use these scans. We developed a pipeline to use MRI scans and convert that into an FE model. So you can see that finite element model up there. It's made of hexahedral elements. It has several tissues, skin, the red part, skull, the blue, cerebrospinal fluid around the brain is green, and then you have gray matter, which is yellow, white matter, which is brown, and then ventricle, which is cavities in the central brain. Those are the blue parts that are filled with the cerebrospinal fluid. Well, the good news is that we just published, like a few days ago, we published our pipeline on our GitHub. So that is the code to our GitHub. So now anyone across the world can go and use our pipeline. See, if you have an MRI scan, you can use our pipeline to generate a brain model in less than half an hour. So I think that is the contribution that we felt we should do to the community. And then, well, we were asking if you want to commercialize it, then no, I oppose to that. I think this is the best way to make sure that researchers across the world can use a brain model in their research. So we have been doing several studies in the last 10 years on understanding the link between strain, and here by strain I mean maximum principal strain and Green-Lagrange strain, because we are dealing with nonlinear mechanics here. So we are measuring, predicting Green-Lagrange strain and the maximum principal value of that across the brain in the duration of the collision or the impact. So one study we did was on rodents. Why? Because this was a much more controlled loading condition than human. In human, often we don't know even what was the loading condition. So you see a finite element model of a rodent head. We drill a hole on the skull, open the skin, drill a hole on the skull, and then hit the dura, the sac around the brain with that impactor. That happens in 0.4 milliseconds, really, really short time. And then we can predict the distribution of this maximum principal strain around the impactor and across the brain. We did quite a lot of work on like MRI imaging 2 weeks after the injury, some histopathology, etc. And with that, we showed that with the strain, even 2 weeks after the injury, that strain that happened at the moment of injury, it can predict almost 70% of the changes, biological changes in the brain in terms of glial activation, in terms of white matter damage and so on. So that was kind of a validation of using strain as a measure of injury. Then we looked into human. This is one of the early studies we did. We had traces from American football impact, from a motorcycle collision, and from a fall. And then we applied that to our brain model. This one is from the American football impact. And then I'm sure you agree that here on the surface of the brain, you see spots of high strain. So brown here means higher strain, and yellow-green means lower strain. These regions, this articulation on the surface of our brain, these are called sulci. So the depth of these wrinkles is called sulci. What is significant about this prediction is that, I don't know if you have watched the concussion movie, the Hollywood movie, it has some traces of truth in it. So they found that some American football players, they change. Not immediately when they are in their career, but when they finish their career, 10, 20, 30 years down the line, they start being a different person, they start being a bit aggressive, perhaps suicidal, and some of them take their life, unfortunately, took their life due to the changes that has happened to them. And then interesting, some of them, it's actually quite sad that they shot themselves in the chest when they want to take their life. Why? Because they wanted to preserve their brain foresight. And then there was a lady in Boston University, she collected all these brains, and then she published a paper which was featured in many outlets. She showed that there is a very specific pathology in the brain of these athletes that doesn't exist anywhere else. So she has been studying Alzheimer's disease, also the neurodegenerative disease for many years. What she found is that this pathology is very characteristic of athletes who are exposed to repeatedly fading impacts. So she found that there is accumulated tau proteins in the depths of soul cell. And then we found the forces are also, the strain is also concentrated in the depths of soul cell. We cannot claim we found a mechanistic link between strain and neurodegeneration that happens 30, 40 years down the line. But it's quite interesting that strain is happening in the same location we see the pathology. We have extended our model to include venous system. You saw the cyclist case, so now this is the venous system we included in the brain model. This is not the cyclist case. We had a rugby tackle where there was microbleed as well. And then perhaps you cannot imagine already, but when you see it, you will see how much a rugby tackler's brain can twist and tear. So this is only in 100 milliseconds of the tackle. And you can see really in the center of the brain how much twisting we can see, and the maximum strains, they're just spreading all across the venous system. And then this is a more recent work that we did. So we're also interested in symptoms. One of them is loss of consciousness. So you know, sometimes in sports, of course in boxing, that is the aim, is to knock out the opponent. In some other sports, this does happen in rugby, in American football. After a collision, you see somebody falls on the ground and lose their consciousness, maybe temporarily, maybe for a longer period of time. A question in neurology that was outstanding was that why this is happening. So two tackles that look quite similar. Why one would lead to loss of consciousness and one would not. So what we did, we had data from a cohort of 20 players with loss of consciousness 40 without. And then we applied that to our brain model, and we predicted the distribution of strain across the model. What you see here is concentration of the strain rates for the group that lost consciousness. And this is concentrated in the stem of the brain. We call it brain stem. And then neurologically, this is the region that controls our arousal and awareness function. So again, for the first time, we could see that actually biomechanics is explaining the symptom. That was quite exciting. We published that in Brain a few years ago. Okay, so here's an example of what this brain model can do. So you can see this maximum principal strain. Starting from the surface of the brain, when the skull starts moving, it's a wave that will propagate towards the center of the brain, reflect, hit the boundary, come back, and reflect several times. This takes around 100 milliseconds, but the first arrival of the wave to the center of the brain is almost 20 milliseconds. So you can see the sort of time scale that we are dealing with here. So you can see Premier League and a device here. This was actually a header in Premier League that we could collect using this device. This device is called an instrumented mouthguard. So this is not a normal mouthguard or gum shield. This mouthguard has sensors, it has accelerometers embedded, gyroscopes embedded, a Bluetooth module, a CPU, a memory, and induction charging. So all of these are embedded within the mouthguard. And this is a technology that can be used now to collect head kinematics in real time. And by head kinematics, I mean 3 translational acceleration along the X, Y, and Z axis, and rotations about the X, Y, and Z axis. And then by having that, we can apply that to the skull and then look at the brain response. So here's another example of using this technology. You see those ladies, the boxes there, and you see here the peak linear acceleration that is measured from their mouthguard in real time. So you see that technology is now really changing the game for us. Previously, we had to do a lot of computational modeling, video analysis, etc. in order to reconstruct the collision. But now with this technology, we can immediately have access to the kinematics. Okay, so now we have the kinematics in real time. We can apply it to brain model and get the results. But the problem there is that these brain models take around 4 hours to 6 hours to run on high performance computing, because they have around 3 million degrees of freedom, and then we need to run it for 100 milliseconds. This is an explicit solver we are using. The stable time instead is around 500 nanoseconds. So you can imagine the number of loops that it has to go through. Okay, in order to address that problem, so we started using machine learning, AI, to look at this problem. So Emily, she had data from a range of sports with our partnership with Sports and Wellbeing Analytics and other governing bodies, where we had access to around 3,000 mouthguard data, head kinematics measured with the mouthguard, and then patiently she simulated all 3,000, which I think took around a year to complete the whole simulations. But now we have a database where we have brain strain, distribution in the brain, as well as kinematics. So now we start using machine learning to link these two. We use two different approaches, convolutional neural networks as well as extreme gradient boosting. And here is the prediction for one of the metrics we use is the 90th percentile strain across the whole brain. You can see it on the y-axis, you can see the ML prediction, and on the x-axis you can see the FEA prediction. The difference is that FEA takes 4 hours, but the ML takes less than a second to make the prediction. And in terms of accuracy, well, there are some points that are still off the 45 degrees line, but still the accuracy is good enough for us to use this technology. This is in the depths of soul size, so we could also look into strain in the depths of soul size where we see the CT pathology, and these are the predictions. One other thing that we had to do is that we have these mouth guards, so we may think that technology is perfect, but it is not perfect. So in Rugby Union and World Rugby, they have enrolled these mouth guards, wearing them as compulsory, but some interesting things are happening. So they use that to call players out if they see that somebody is exposed to high acceleration. There have been cases that they call out the player and they're like, I didn't do anything, even there was no tackle, but they review the video and they see that the tackle happened 20 minutes ago. So this is a limitation of transmission from the mouth guard to the receivers, and something that is not easy to solve. So there are like 20 players on the pitch, there are a few receivers around the pitch, but there are so many complications. So 20 mouth guards working at the same time, busy collecting the next impact. There could be 2 consecutive impacts, but at the same time, the mouth guard should decide whether it wants to analyze it, whether it wants to send it to the receiver or not. So there are so many complications. One thing we found is that we have to make the computation as light as possible on the mouse guard chip. And that's why we found that using CNN, convolutional neural network, maybe is not the best option. So if you look at flops, so floating point operations, the number of flops with our XGBoost model is 10,000, is 1,000, but with CNN, it's orders of magnitude bigger. So it means that CNN is not really an efficient approach, while both of them are giving similar accuracy. So again, being in design engineering, that is one thing that we always look into, is that what is the actual use case and how people are going to use it in real world, rather than I have a good technology, let me push it into an application. So that was really working on that backward problem. We work with the technologies tools for producing this mouth guard, as well as governing models, to understand that this is actually a bottleneck. All right, so even we have gone further. So I mentioned in design engineering, we're as well very keen to see now how people can use the technology. So you see Elena there, she's a PhD student in my group, and she was very keen on turning that machine learning model into an app, and she has already achieved quite a lot. So you can see the app, it's been now, the name is Trace, and we have an online version of the app, which I will show you in a second. So if you go to Elena's GitHub, we have an online version, and this app now is able to connect with MouseGuard Live, but unfortunately I don't have a MouseGuard here to demo it, but we have already some preloaded MouseGuard data. So let's say if I choose one of these, for instance, I can go with, you see we have boxing, mixed martial arts, and rugby football union. So I use rugby football union. These are the traces that were collected in the mouth guard, and these are the predictions from the brain model in different tracks. So these are the white matter tracks, the wiring of the brain I mentioned. So this is in a split of a second. This prediction is done, and we can look into the brain, across the brain, different regions, and this is the value of that maximum principal strain provided. So for whole brain is 0.5. In different tracts, we have a prediction of this strain. All right, so back to the case. I show you this cycle collision. Well, they were not wearing a mask, obviously. So then we had to use multi-body dynamics, which I'm sure you're familiar with. So we could represent the car with the right stiffness, contact properties, as well as the cyclist, bicycle, in order to predict the speed of the head-ground impact. And then we use that speed and the location of impact to go in our lab. We have a helmet test rig in our lab, which can test all sorts of different helmets. But in this case, we tested cycle helmets with that hybrid 3 headphone, with accelerometers within the headphone. So we measured the kinematics from that. And then we applied the kinematics to our brain model. So this is what our model is predicting that had happened to the brain of that cyclist in the venous system. And you can see in certain locations there is more strain in the venous system. You can see in this location, for instance, there is a bit of concentration. And then actually that was quite encouraging, because that is exactly the same location where we see microbeats. So again, it's providing more evidence and validation that our brain model is able to roughly predict the location of injury. But of course, this is one prediction. So we need to, of course, extend this to many more cases. All right, so the reason I mentioned that is that another part of our application of our research is in helmet testing, not design, but testing. We do not design helmets, but we test helmets. The tagline is that helmet standards are outdated. Perhaps you need to delete me on that. Standards were generated like in 70s. There was one standard in the UK, motorcycle standard. Everybody else started copying the same standard. Even, to your surprise, for pilots who go through ejection from the aircraft, they're using the same standard that you're using for motorcyclists. So what I mean by standard, the loading condition, so how they drop the headform, as you saw there, we put the headform in the helmet, we drop it, they drop it on a vertical angle, and they measure peak linear acceleration, which you know is a measure of skull fracture and not more diffuse brain injuries. What we found, one of my students is now a consultant in Royal Air Force. He found that in the last 30 years of ejections, he found 300 ejections, and he showed that loss of consciousness is the biggest concern for pilots when they eject from the aircraft. And you know, if a pilot loses consciousness, that is really dangerous, because they can be exposed to many threats. So he went on to design a new standard that is measuring risk of loss of consciousness, and that standard was published 2 weeks ago by the Royal Air Force and MDQ. So really another example as to why standards are already outdated. The other problem is that you're faced with a range of claims by designers, helmet designers. They come out and say, my helmet is MIPS killer, that's the first one. My helmet is 50% better than the others. But really for consumers, that is extremely confusing. Even for me, as an expert in this field, that is extremely confusing, because I don't know even how they measure what they mean, mine is 50% better. So we definitely need an independent, scientifically based comparison that is accessible to consumers. So if you go to a bike shop and you want to buy a helmet, all helmets on the market have passed these outdated regulatory standards. But you don't know if a helmet that is 150 pounds is more protected than a helmet that is 20 pounds. You are not given that information. And I show you that you cannot use price as a proxy. So we took the adventure, we developed a consumer-facing rating system, we branded it as Hyper, Helmet Impact Protection Effectiveness Rating. So Hyper has 3 main pillars. One is the anthropometric test device or headphone that we are using. Second is the impact conditions. And third is then how do we interpret the measurements from the headphone. So good news is that after 30 years using an aluminum headphone that was representing an average American male, we have headphones that are better representing, well, still with a caveat. These are Europeans, so this is 200 MRI scans in Europe, but still, it is representing male, female across different ages. And you can see even children, it's not a scaled down version of an adult. It does look like a child. that is a problem. So if you current headphones, you look at them, there's an adult and the child is just a scaled down version of it, which is not anatomically correct. And the other factors that we looked into was coefficient of friction, mass, center of mass, onset of inertia. I will not go into details, but anyway, we published that standard back in 2024, and that is now available for anyone across the world to adopt. And 2 manufacturers are making these headphones, and we decided to adopt this for our rating system because this is the most by Fidelity headphone so far in the world. What else we did? We didn't want to continue what standards are doing. We looked into actual accidents, and we had around 815 data points from literature, and from that we found which locations on the head are impacted most, and even we could have a weighting for different locations. So you can see here, for instance, if you look at the average, the last columns, you can see the front is impacted most, and then we have crown impacted least, and then we have sides, and then we have the rear. So that weighting you will see later is being used. So based on that, we set up these impacts. So you can see we do 4 impacts. 1 is on the side, 1 is on the front, 1 is on the front side, and 1 is on the back. So we do 4 different impacts, which is aligned with the new revision of the standard not published yet. And from this, we make measurements. Measurements of linear acceleration, measurement of rotational velocity. So these can represent 2 different categories of brain injuries. We have risk functions from literature, so we can put the peak linear acceleration, translational acceleration on this curve, and find the risk of so-called linear injuries. These injuries are skull fractures, focal brain injuries, anything that is more linked to direct force on the head. But we also measure risk of rotational injuries. So these are injuries that are explained a bit further in my talk. And these are perhaps even more important than skull fractures. We had a meeting right here. We had a very experienced neurotrauma surgeon who was here. And then there were people from industry, etc. They were asking him, in your opinion, what is more important? He was saying that if I have a patient with skull fracture, perhaps even I will send them back home. I'm not too much concerned. But if I see a patient that has diffuse brain injuries, I do not know even what to do. But I will do my best to make sure that I can control it, because that is the injury that will change the person forever, not the skull fracture. But to your surprise, and maybe you already know that, none of the standards at the moment are measuring rotational injuries or rotational metrics, except from EC 2206. There's one motorcycle standard that has just started to monitor. All right, so once we have this, we have risk of linear injuries, risk of rotational injuries. We have the weighting from different 4 impacts. Then we apply the weighting to these risks, and then we sum them up. So we have an overall risk for every helmet based on the exposure, weighting, and 2 different types of risk. So we had limited budget. Of course, we do not have unlimited budget. We had limited budget to buy 30 helmets, and on each helmet we had to do 12 impacts. So in total, 30 times 12, 260 impacts. So there are a range of helmets on the market. How do we choose them? We ran a survey, and we asked cyclists to tell us what is their favorite helmet. So based on their survey, as well as so we collected around 1,100 data, and we continued that. At the moment, we have 2,000 data points. We have written papers only on that. And bestsellers list, we chose 30 helmets that are most popular within UK cyclists. These are all the helmets that we have chosen. And then we did this study, we did the test, we rated them, and here are the results. We have the overall risk. So each line is representing 1 helmet. Here we see the linear risk, here we see the rotational risk, and here we see the average of these 2. What is quite interesting is that linear risk, the spread is not as large as rotational risk. See, there is much bigger spread in rotational risk. And then one of the reasons we thought could be that standards are only enforcing this and not that. So manufacturers do not have to control rotational risk. And as a result, we end up with solutions that have very different rotational properties. But when it comes to linear risk, they are optimized. So I was talking to manufacturers, they were telling me that they spend almost 80–90% of their budget to optimize their helmets for the standard, which is the linear risk. Which is a shame, because we know rotational risk is important, but we see so much disparity. Here's the difference, actually. So The one on the left is a helmet with low rotational risk and low overall risk, and the one on the right is the helmet with high rotational risk. So this is the one with high risk, this is the one with low risk. What is the difference?
You can see relative motion between the white helmet and the sky.
Yes. And then that helps, right? Because here you can clearly see.
Do you want to play it again so everybody can see?
So
The twist of the head is more serious.
yeah, rotation of the head is much bigger in this one compared to this one. And that's because the helmet. So you see the helmet here is sliding on the head. There is a slip layer within the helmet, this yellow layer, maybe you've heard of it, it's called MIPS. So that kind of disengages the head from the head forming rotation, allows the helmet to rotate, but it can prevent the head rotation quite a lot, as you can see here. But that helmet is coupled really tightly with the head, so it doesn't really allow much helmet rotation. And as a result, there is a lot of rotation of the head. And if you look at the risk of rotation obviously is much bigger in that. The other point, we have overall risk here for all the helmets, and here you have their price. And I hope you agree that there is no correlation. Right? It doesn't tell us that higher price means better protection. Even you have some helmets that is 130 pounds and it's really high risk. This one is only 36 pounds. It's one of the lowest risk. And actually, I bought 4 of these from myself and my family. And I see Bob, I think he has one of these, and some of my colleagues, I see they are having one of these 3 helmets. I see it quite a lot in the department, which is another proof that this rating has been successful. I see people that are choosing the helmets that we rank as the best helmets, and perhaps not most expensive. Okay, but what is important is that we need to communicate the results with consumers. It cannot remain in a paper or in a couple of conferences. That's why we took again the challenge to develop a consumer-facing website. Our website is here. You can scan the QR code, or you can go to hyperhelmets.org and you can see it for yourself. So on the website, we provide a list of 30 helmets. In each helmet, if you click on that, you can see the risk scores. You can also see high-speed videos from the test. You can see the helmet in action. Well, this is 30 helmets. Of course, our ambition is now to extend it beyond that. The rating has been very successful, so we launched it in 2024, almost 2 years ago. Our website has been seen over 150,000 times across the world, with UK, US, Canada, Australia, and Germany having the most views. A major UK retailer changed price of their helmets due to this. They contacted us. Now we are collaborating. They have already donated some funding for us to buy helmets. And there is a possibility that they will use our rating on their products in future. So we are already in contact with them and discussing with their branding and business departments. Major helmet manufacturers engaged with us after this, so Specialized, Cask, Scott, Trek. There were a range of helmet manufacturers that contacted us, and interestingly, they're asking us how can they submit their helmet before they send it to the market, so it's rated, and when it goes to market, they have our rating on their product. And the paper that we published, it received the Best Paper Award of Annals of Biomedical Engineering. It has already been accessed 16,000 times in 2 years, which is quite unusual. So all of this, the rigor of the work and the actual impact that it's already had, it led to Prince Michael International Road Safety Award that we received last year. As I mentioned, the best research article of Annals of Biomedical Engineering, and actually we've just been informed that we received the College President's Excellence Award for research impact. All right, so what is next? Our vision, I don't know if you've heard of your NCAP. Have you? NCAP in general, global NCAP? Because there's also like China NCAP, US NCAP, global NCAP. Well, if you want to buy your car, you want to spend a lot of money, but if you're interested in the safety of your car, you can go to one of these NCAP websites and you can see the testing of the car. And you can see the scores that they give to different features of the car in terms of like assisted driving systems, passive protection, active protection, pedestrian protection, cyclist, child, etc. And you see all the scores and then the overall rating of the car. And this is quite worldwide. It's been 20 years they are running it, and they're claiming now that they have saved over 10,000 lives by the race. Our vision is to be Urania. And the good thing about them is that they are not for profit, and they are funded through their testing as well as some big organizations like FIA Foundation and so on. That is our vision, but how we move towards that is still a question mark. So we have already had more funding from Road Safety Trust to extend our rating. We have tested 30 more helmets. One question now we're asking is that how collapsible helmets compare with conventional helmets. You know, now with micromobility, shared bicycle scheme and so on, people may prefer to put a helmet in the back in case they want to use it. They just don't want to carry a bulk helmet with them if they happen to use a bicycle. And we have very interesting results from that we will share with you later. We are going to open our rating to manufacturers. So far we have not done it. We have kept them at arm's length because we know that they can send a helmet that is different to the helmet that they send to the market. And now we are putting a declaration of conformity document together which has to be checked by lawyers, etc. But to make sure that they confirm the same helmet they send to us will go to the market. We are extending hybrid to children's cycle helmets. That is the work that we currently are doing, and next year we are going to publish our results. And extending hybrid to other helmets. So we already have done some work on motorcycle helmets, and we have discussion with the Christian authorities. So this is happening. But really the question is that how can we sustain hybrid? Any recommendations? That is really an open-ended question. But if you think immediately of any, of course, if you have some loose cash, but I mean cash in the order of hundreds of thousands, that can help us to move on. But our vision, as I mentioned, we want to possibly spin it out from Imperial as a not-for-profit organization in the future. And with that, I want to acknowledge all the funders and collaborators in this work. And one of the interesting initiatives, perhaps you can look up the website. TBI Reporter is a national platform, £10 million platform funded by UK RR, so research, what does it stand for?
UKI, the United Kingdom Research Institute.
Yes, yeah. So this is the government's research funding. So that is funded by the Alzheimer's Research UK and Ministry of Defence. And the idea of TBI Reporter is that there are so many work that is done, but the data is kept in silos. They want to be a display for the data that can be combined to answer different research questions. And we are the only engineering group across 50 investigators that are providing biomechanical information. They've already linked the UK electrographic collisions database rates with the TBI Reporter. So if you are interested in this domain, you can look up TBI Reporter as well. Well, thank you for your attention.
Thank you. So we have a few things. We have an opportunity for questions, which we will do first, and then we have a presentation for NASDAQ. So, ladies and gentlemen, any questions? Please.
Question here.
And say your name and affiliation.
My name is Jay. I'm from ABB in Germany. I have two questions. The first question is what kind of material I guess it's a hybrid material.
It's hybrid viscoelastic.
Okay, that's great, because at the end you show that the concussion of the brain, basically the consciousness of this, is dependent also on the rate of the strip.
Yes.
So if you only use hybridistic material, or you will not capture that material behavior, basically only based on the impact speed, then you can only use the speed of the strip. But it has not used the visco.
Yes, so the term model we're using, so this is a huge area of brain biomechanics. It's all about characterizing brain mechanical properties as well as finding the right constitutive model, even developing new constitutive models. But what the field is now agreeing on is that we have to have hyperelasticity because brain is non-linear, but we have to have also viscoelasticity. And the models that we are using here, we are using all of them, but then we also use linear viscoelasticity. These are two are combined.
Okay. The next question is, in the machine learning correlation, you say the accuracy, etc. My question is rather, you have the loading profile from the acceleration sensor. That's fine for me, but your brains consists of different kind of brains, not only one brain. You know that many times. How did you consider the finite elements difference there, right? They are totally different geometry, and then how did you really correlate these aspects in that chart?
Yes.
Right? Or even the three-dimensional acceleration. How did you at the end to somehow to reduce the quantity in one parameter, or is your method there?
So, if I understood, I think you're referring to the fact that all of us have different heads and brains.
Yes.
And so the anatomy obviously is very different, and material properties can also be different.
Yes.
So yes, we have also gone on that adventure. So we had around 200 subjects with different brain volumes. So previous research has shown that total cranial volume is what that can have most effect with some principal component analysis. It can have some most effect on the strain prediction. So then we chose the subjects across a wide range of the total cranial volumes and then exposed them to some of these impacts that they are from sports. And that data, we found that the majority of them, the difference is around 10% in terms of strain prediction. But there are also cases, it's true that there are cases where this difference can go up to 30%. So it could be that individual impacts with individual head shapes that you might be missing if you use this generic approach. And that is this is still an outstanding problem. So the problem is that how can we individualize these machine learning models, which is an outstanding problem.
Yeah, thank you very much for this very
Great questions.
fantastic work. Yeah.
Thank you very much. Any further questions? I'm interested. I'm going to provoke you. We have 5 more minutes for questions. There are brain researchers in this room looking at things other than rotation. I just wondered, let's just see whether we can provoke any other questions. Yes, please.
You mentioned that first time for a really interesting topic. For the mouthpiece, actually, I have a question. So based on the acceleration data of that mouthpiece, you kind of correlated to amount of rotation and the linear motion of this. But is it also can predict the location of the impact, or is it important at all in this
Okay, that's a very good question. We have acceleration at the sensors, and then these are linear components that are transmitted to the center of gravity. The rotation, we don't have rotation, doesn't depend on the center where we're measuring the accelerations. In terms of finding the location of impact, there has been some research to suggest what was the direction, but location at the moment is not possible. But one thing that is quite important is that we see in the sort of cases we look at in sports, the direct impact on the head doesn't seem to really determine the outcome. Because the impacts themselves, the direct impacts are limited, they are small in magnitude. Also, several of these cases are non-impact accelerations. So we call them head acceleration events, not impacts, because they are like tackles. So if you tackle somebody shoulder to shoulder, then head will, it's like a whiplash effect. But you're right, so there are cases as well where the location is important. For instance, in boxing, if the punch is on the mouth guard or on the jaw, it can influence the measurements of the mouth guard. So there are definitely data that we have to scrap at the moment. So it's not that all the data is useful. There is always video checking and analysis, so we make sure that these are true impacts. So we make sure that we only include the true positives in the simulations. But yeah, there are still some technological challenges. Thank you.
My question is in the brain, it's not simply related to the damage of the tissue or damage of the brain part. It's also related to the functional connection, or maybe some conditions or combination problems that may not be able to replicate from no matter MRI or MRI signals. So, have you considered this kind of conditions that may not be able to replicate from MRI or MRI? Have you considered these kind of things?
That's a great question. So you're absolutely right. So we have brain is really complicated. So of course, brain has to function, function, like cognitive function, etc. This is based on the connection, based on how the neurons are firing, linked, etc. There's also a bit of the biological part of it, which is what potentially we can see on MRI scan. But the truth is that most of this impact, by definition, they are called mild traumatic brain injuries, and by definition, you cannot see anything in the brain in MRI. Even if you use the most advanced MRI scans, it's highly likely that we will not see anything, any changes in the brain. And always the outstanding question is that how can we then link loading with some biological changes in the brain? One way is to use cognition, but that is very complicated because we are passing several layers to reach the cognition. One technology we are at the moment using, which is really exciting, this is blood biomarkers. So now there is more and more research to show that with just a tiny amount of blood, so 0.5 milliliter of blood, we can detect proteins that are supposed to be in our brain. When they happen to be in the blood, it's an indicator of exposure to large forces. And this technology is now scalable. So there is like patches you can put on your arm and self-administer to collect the data. We send it to biomarker factory, and then we get all the analysis, and we know which proteins are elevated. So that is actually what we are using in a larger scale rugby study now we are doing in the UK, where we are instrumenting 600 players, 50% female, 50% male, in order to look into how much strain is enough to trigger this blood biomarker elevation.
Ladies and gentlemen, can we thank Mazdak once again?
Thank you.
With the banner, we have a fancy artifact for your office, and thank you very much.
Thank you.
Thank you.
And wonderful to see you. We have coffee break now. Can you stay around for 20 minutes? So please chat to Mazdak and each other, and we'll start again at 10:30.
Yeah, at 10:30. Yeah.
Okay.
Mhm.
Thank you. Wonderful. That's thrilled to hear.